Alrighty, good morning everybody. Welcome back to Count 3. Reminder, please wear your masks during class. Plan for today, we're going to finish off Standard 2. Finish our discussion of dot products, which we started in class on Wednesday. Office hours. Just so you know, my office hours for next week are completely screwed up. I'm on 2 different faculty searches, which means I'm going to be interviewing 3 different candidates next week, all of whose interview times are basically scheduled to be right in the middle of my office hours. Thanks, Provost's office. Which basically means there's going to be a lot of non-standard office hours. And I tried to add, and time's missing. I tried to add a couple extra hours to make up for that. So on Monday, I'll have office hours the hour before class, and for a good old 20-minute period from 2 to 2:20. And as far as homework goes, we are going to have a Standard 2 quiz on Monday, start of class. Black Arsenal, so about Standard 1 quizzes. I didn't grade them yet. Decided until I'm fully vaccinated, I'm going to wait a few days to actually grade quizzes. Waiting 3 days. I'm basically giving it a 3-day waiting period between when you turn in quizzes and when I'll grade them. Just for COVID safety mainly. And so I'll grade your Standard 1 quizzes this weekend and get those back to you on Monday. Retests. Some of you have started emailing me about retests. We're going to start doing retests next week, and I'll send out some information over the weekend about how that is going to work. But if you want, basically, as a quick reminder, the way it'll work is you'll request a time to come in and take a retest, and there'll be a 10-15 minute period where I'll put you in a private room, and you'll basically just take a quiz similar to the one you already took for that standard. But I'll talk more about that email I sent out over the weekend and in class on Monday. And then also on Monday, we will start Standard 3, which will be about cross products. The final kind of vector algebraic operation we're going to be looking at, and the most complicated, and in my opinion, the most fun. Does anybody have any questions or comments before we get started for today?
We can retest no matter what our grade was on the original standard quiz, right?
Indeed. Because no matter how well you did on the original quiz, you will either have 0 or 1 masteries on Standard 1. And so you will be able to retest. You will need at least 1 more retest regardless on that. The only time you can retest on whatever you want throughout the semester. The only time I say you shouldn't retest on something is if you already have 2 masteries, which won't be the case until at least after your first retest or the first exam. There are questions or comments? I don't know if you all noticed, when I was walking down the hall to come in here, I actually saw Dr. Arm walking down the hall. He had a weird grin on his face and was holding a sheet of graph paper. I don't know what that was about, but I think he might be plotting something. Okay, so last time we talked about the dot product and kind of talked about a couple different reasons why we would care about it. As a reminder, if we have 2 different vectors, v and w, and rn, we define the dot product to just be the scalar value we get from basically multiplying their respective coordinates together, v1 times w1, v2 times w2, etc., and then adding all of those little products together at the end. And the 2 reasons we talked about why we care about the dot product is it lets us find the length of a vector v, which is just going to be the square root of v1 squared plus v2 squared up to vn squared, which, if we wanted to write using the dot product, we can get using the square root of v dotted with itself. And finally, the dot product gave us the way to find the angle between 2 vectors in Rn, where if you have a v and a w emanating from the same point, the angle theta between them has to have a cosine equal to the dot product of v and w divided by the product of their magnitudes. Magnitude of v times magnitude of w, where magnitude and length refer to the same thing. And so, theta, we're always going to be considering, again, using radians, and we're only going to be looking at values between 0 and pi for theta. Because technically, with 2 angles like this, you could say something about, Dr. Gerstle, what if we consider this to be our angle between v and w? I mean, yeah, we technically could, but I don't want to. So we always are going to consider theta to be the smaller angle between V and W, not the angle greater than 180 degrees or pi radians that we technically could do, but we don't want to. So what I want to start with today is to talk a little bit more about this angle between V and W, and in particular, I want to look at kind of an exercise where if we only know whether the dot product of V and W is positive, negative, or zero, what can we say about the angle theta? I think you were asking about this last class, like knowing whether the dot product is positive or negative, what information does that tell us? It's going to turn out that that tells us quite a bit about theta. So I'm going to be on page 1, 2, 3, 4 in the packet. And what I want to ask the question of what can we say about the angles between two vectors A and B if the dot product of A and B is greater than 0? What does that tell us about theta? Well, let's take a quick look. If A dot B is a positive number, we can say that cosine of theta, which is defined to be the dot product of A and B divided by magnitude of A, magnitude of B. If A dot B is positive, we're going to know the numerator of this fraction is going to come out to a positive number. What can we say about the magnitude of A times the magnitude of B in this scenario? It's also going to be positive because the magnitude of the vector, its length, is always going to be a positive number. Unless it's the 0 vector, but if it's a 0 vector, then this dot product can't be positive. So we know cosine of theta is going to be some positive number, the dot product, divided by another positive number, the product of the two magnitudes, which is going to tell us then cosine of theta has to be some positive number in order for the dot product to be positive. Positive over positive equals positive. And if cosine of theta is a positive number, what can we say about theta? Heads up.
Between 0 and
Yeah, it's going to be between 0 radians and pi over 2 radians. If you look at your unit circle, assuming we're only looking at the first two quadrants in the unit circle because of this restriction, we don't care about quadrants 3 and 4. This is quadrant 2, this is going to be quadrant 1, and who cares about what's down there? If cosine of your angle theta is some positive number, that means we have to be in quadrant 1. And so theta has to be in between 0 and pi over 2. Now, if theta has to be between 0 and pi over 2, we could ask the question, could theta be 0 exactly or pi over 2 exactly? So if cosine of theta is a positive number, could theta be equal to 0? Oh no, Dr. Gerson's making us think in trig. Or maybe I should reformulate the question. Is cosine of 0 radians going to be a positive number? Yeah, cosine of 0 is 1. If you look at this point corresponding to theta equals 0, this point has a very much a positive x coordinate. The cosine of that angle, 0, is going to be positive. It's just going to be 1. So theta is allowed to be 0. Can theta be equal to pi over 2?
No, because that's 0.
Yeah. Cosine of pi over 2, meaning this point up here, is going to be exactly 0. So if the dot product is positive, theta itself cannot be pi over 2. It can be 0, but it can't be pi over 2. And so theta has to be some angle in between 0 and pi over 2 radians. Or if you prefer, it has to be between 0 and 90 degrees. So what does that tell us about the angle theta? What type of angle is theta going to be? It's going to be some angle that's less than 90 degrees. Bingo. So theta is going to be an acute angle. It's acute. Which means you're going to have a picture like this one. Where A and B are closer to pointing to the same direction than they are to pointing in opposite directions from each other. Since the angle between them is less than a right angle, it's acute. Any questions or comments about that one? So what changes if we allow theta, or if we have a dot product, that's negative instead of positive? Well, in this scenario, cosine of theta is still going to be dot product of A and B divided by magnitude of A times magnitude of B. Our numerator this time is going to be negative for cosine of theta. What about magnitude of A times magnitude of B? Is that going to be positive or negative in this scenario? Still going to be positive for the same reason as before. Lengths of vectors are never allowed to be negative numbers. So cosine of theta is going to be something negative divided by something positive, which is going to tell us then cosine of theta has to be a negative number this time. The reason being, negative number divided by positive number is always negative. The denominator was also negative, then it'd still come out positive, but that's not the case. And if theta has a cosine that is negative, meaning in this graph we're looking at points in the second quadrant, what can we say has to be true about theta itself? Let's get someone from the right half of the classroom involved. Hearing a lot from kind of these left two columns. Theta has a cosine that's negative. What two values must theta be between?
Pi over 2 and pi.
Pi over 2 and pi. Indeed. Can theta be? Theta cannot be equal to pi over 2 from the same reason as before. If theta is pi over 2 exactly, then the cosine would be 0, not negative. Can theta be equal to pi? Yeah. Theta's out here. That's a point with a negative cosine. The x-coordinate is -1. So cosine of pi is -1, so that's acceptable. And so this is what ends up having to be true about theta in this context. That theta has to be greater than pi over 2 radians and less than or equal to pi radians. Or if you prefer, theta has to be strictly greater than 90 degrees and less than or equal to 180 degrees, which tells us theta has to be what type of angle? Has to be an obtuse angle. Or straight angle. Straight being at a 180 degree angle. Because if you have a 180 degree angle, technically that's called a straight angle and not an obtuse angle. So in this scenario, our theta is going to look something like this. Here's our A, here's our B, Or potentially something like this, where here's A and B is pointing in the exact opposite direction. So if our dot product is positive, we get an acute angle between the two vectors. If the dot product's negative, you get an obtuse or a straight angle. Meaning, in the case where the dot product is negative, the two vectors are closer to pointing in opposite directions than they are to pointing in the same direction. Finally, let's take a look at the case where the dot product is 0. Well, in that scenario, cosine of theta is going to be dot product of A and B over magnitude of A, magnitude of B. Well, this is going to be 0 divided by, who cares? It's 0. And what possibility does that leave us with for what theta could be? If there's only a single value theta could take on if it's in the first two quadrants and has a cosine of 0.
It can only be pi over 2.
It can only be pi over 2, indeed. Pi over 2 radians, or 90 degrees. So, if the dot product of A and B is 0, what type of angle are we going to get then between A and B? Has to be a right angle. Something that's going to look like this. So, depending on the sign of your dot product, whether it comes out to positive, negative, or 0, you could say a lot about the relationship between your two vectors. Namely, how close are they to pointing in the same or opposite directions? And if your dot product is 0, that means they're perpendicular to each other, meaning they're equally far apart from pointing in opposite versus the same directions. It's a good workout for teamwork. Any questions or comments about the relationship between the dot product and theta here? Okay, so in that case, I want to talk a little bit more about this perpendicular condition. So, turns out we only really have good visual intuition, I think, for what does it mean for two vectors to be perpendicular in R2 or R3, meaning they have a 90-degree angle between them. But we can generalize this idea of perpendicularity to even higher dimensions when it doesn't make sense to think about what does the angle look like. And that we can actually define two vectors to be perpendicular, or, if I may be allowed to introduce a fancy new word, orthogonal to each other, by using this condition. Two vectors are orthogonal if their dot product is 0. So let's write that down. We could say vectors A and B are orthogonal or perpendicular to each other if the dot product of the two vectors comes out to just be 0. And this works for any Rn. It can work in R2 or R3, where you have a nice visual intuition of orthogonal, perpendicular just means right angle. But you can also talk about two vectors in higher dimensions, and R4, R5, R5 billion, still being perpendicular to each other through this definition, even if you don't have any sort of good visual intuition as to what does that actually mean about an angle between them. So we saw an example last time of these sorts of perpendicular vectors. In R2, we saw an example where we looked at two vectors 2, 5 and negative 10, 4. So we can say 2, 5 is orthogonal to negative 10, 4, since their dot product is 0. You could also say something about vectors in, say, R4, where for the same reasoning, we could say that 1, 2, 3, 2 is orthogonal to negative 1, negative 2, 1, 1, because 1 times negative 1 is negative 1, 2 times negative 2 is negative 4, so we're at negative 5, plus 3 is negative 2, plus 2 is 0. These are orthogonal since their dot product is 0. The key difference here, though, is in R2, we have a good visual intuition as to what that means. If I draw out these two arrows for 2, 5 and negative 10, 4, we can see the arrows have a right angle between them. Whereas for our two vectors in R4, it's a lot harder to try and visualize what does that actually mean intuitively. And it's going to turn out to be the case in a couple standards from now, in standard 4, even if we don't necessarily have a good visual intuition for what does it mean for two vectors to be perpendicular, it's still going to give us some useful algebraic information about the way that the vectors interact with each other. And that's going to be used in standard 4 to help us define hyperplanes. Thought planes are cool, hyperplanes are hyper. So what I would like for you all to do now is to work on a couple questions on your own. And if you feel comfortable doing so, you can work with the people sitting around you, though you certainly don't have to. I would like for you to answer the two questions I have on this page. Namely, find the value of C such that these two vectors are perpendicular in R4, and find all vectors in R2 to which 1, 3 is orthogonal. Find C, so V equals 1, 0, 3, 6, and W equals 3, 5, negative 2, C are orthogonal in R4. And on the other side of the board here, to which vectors in R2 is 1, 3. Let's go ahead and take a couple minutes, see what you think about these two problems. If you feel comfortable doing so, like I said, you're welcome to work with your neighbors or to ask me any questions you might have. And in a couple minutes, we'll come back together and talk about these as a class. You're missing something. Those are correct answers, but not the only ones.
Yeah.
And I'll give you a hint. For the second question, which vectors in R2 is 1, 3 orthogonal, there's more than 2 of them. Sorry, smell into the camera. Could be. Why is that? Ah, take scalar multiples. It's a good idea. Might be onto something. You're missing something.
I'm sure there's more.
Infinitely many, in fact.
Yeah.
So the question is, how do you write them all out, so to speak? Let's give it about another minute, and then we'll come back together and talk as a class. So let's talk about the two of these problems. I saw some interesting ideas as I was walking around the room just now. Like several of you had some ideas about how you would find what value of C is going to make these two vectors orthogonal to each other. Anyone like to share their thought process for how they approach this one? All right. So we set the dot product equal to 0. Just a minor nitpick in what you just said. We technically say the vectors themselves are what are orthogonal, not the angle between them. Angle between them is a right angle, I would say. But yeah, I like your idea. We're gonna just take the dot products and set it equal to 0, and then we can see what would C have to be in order to make that happen. So we could say if B and W are orthogonal, then it has to be the case that 0 is equal to their dot product, which, writing that all out, is going to be 1 times 3 plus 0 times 5 plus 3 times negative 2 plus 6 times C. Which, if we simplify, is going to give us 3 minus 6 plus 6C. So that we end up with 0 is equal to negative 3 plus 6C. And that is going to give us a linear equation. Something in Algebra 1, I'm guessing, that you've had to solve. Like, negative 3 plus 6C is 0. What must C be? So if we solve that equation, anyone tell me what they found for C? 1/2? I think so. As we add 3 to both sides, we'll get that 3 is equal to 6C. And if we divide both sides by 6, we'll get C is equal to 3/6, which when simplified will give us 1/2. Dr. Gerstle, if I said the answer to this question on a quiz was 3/6, would I still get credit? I would. That is correct. 3/6 is correct, and I would give it to you, but it would make my heart ever so slightly disappointed that you didn't simplify it. Any questions or comments about this one? This one you all seem to struggle with a bit more. How can we find all the vectors in R2 to which 1, 3 is going to be orthogonal? Okay.
Any scalar multiple of the displacement vector, negative 3, 1.
Ooh, any scalar multiple of of that one? Why is that?
Because that vector is perpendicular to the original vector. But it's not just that one, it's any scalar multiple you can take of that, and it's also starting at any point on the plane.
Okay, starting at any point on the plane. Yeah, so geometrically, I think it doesn't matter here whether we're talking about position vectors or displacement vectors. In fact, I'm going to make a comment on that once we get through this example. But I think Sarah's onto something. So what I did for this one is I set up an equation like I kind of did over here and set 0 equal to the dot product of 1, 3, and something else. I said if AB is, I'll say, any such vector, then it would have to be the case that 0 is equal to the dot product of 1, 3, and AB, which if we write that out, is going to give us that A plus 3B is equal to 0, or that A is going to have to be equal to negative 3B. And so if we want to say, well, any vector A comma B where A equals negative 3B will do the trick, we could write that out by saying, place this in the middle. We can do that by saying 1, 3 is orthogonal to any vector of the form negative 3b comma b, i.e. to any scalar multiple, which we could write as being b times the vector negative 3, 1, which means 1, 3 is going to be orthogonal to any vector that's a scalar multiple of negative 3. I think I agree with your answer, Sarah. Nice job. That if we were to take negative 3, 1 and any scalar multiple of that, because if b is 1, this works. If b is 2, if b is 5, if b is 17 billion pi, if b is negative 3, all of these would be vectors that would make that would be of this form for some value b, and thus would be orthogonal to 1, 3. Geometrically, you can see that by basically just trying to draw a graph of what does 1, 3 look like and what the vectors does it look like it's perpendicular to. If we did that, let's say here's our x, here's our y, 1, 3 is what we started with. So if this is our vector 1, 3 right here, then the vectors that are going to be orthogonal to it are basically going to be any vector that would form a right angle with it. So a vector like this, or like this, or like this, vector like this, or like that, or like that. All of these are going to be examples of vectors that are perpendicular or orthogonal to the original vector 1, 3. And so it turns out that geometrically speaking, the set of all vectors orthogonal to 1, 3 is going to be an entire line's worth of vectors if we treated them as position vectors in the xy plane. So like this one, for instance, might be like 3, negative 1 right here, and any scalar multiple of that. So you could stretch it out to be as long or short as you want. You could flip the direction and change the length as well. Any of those will give something that's orthogonal to the original vector 1, 3. Tim,
I'm good, never mind. I figured it out.
Okay. So, looks like we have an entire line's worth of vectors that are going to be orthogonal to 1, 3. And I think Sarah mentioned it could be a displacement vector as well. So we could say something like this vector would also be orthogonal to 1, 3, even though they don't start at the same point. Because algebraically, this vector, pretend this has the same orientation. This vector, algebraically, if we were to write out numbers for it, would be the same as one where we could start it at the origin and would still be on this line. So question. If in R2, the set of all vectors orthogonal to 1, 3 looks like a line, does anybody have a guess as to what the same thing might look like in R3? If we were to look at the set of all vectors orthogonal to, say, 1, 3, 5. It's going to turn out to be a plane. An entire 2-dimensional surface's worth of vectors. And that's going to be something we'll look at in detail and study when we get to standard form, which is all going to be all about lines and planes and how do we write them down. So, kind of gives a sense of how orthogonality works. Here's an interesting question, in my opinion. What's going to be the set of vectors to which the 0 vector is orthogonal in R2? According to the definition of orthogonality.
According to our definition, every vector in existence would be orthogonal. Because if you multiply anything by the 0 for the dot product, then it would always be equal to 0.
Yeah. It's going to turn out, unlike with 1, 3, in which case we had a line's worth of vectors that would do the trick. In R, if we ask the question of which vectors in 0, 0, to which vectors is 0, 0 orthogonal, the answer is going to be all of them. Since any vector AB is going to satisfy, if we take the dot product of A comma B with 0 comma 0, we're going to get A times 0 plus B times 0, which is going to give us 0. So no matter what vector in R2 you pick, if you take the dot product of that vector with 0 comma 0, the output is going to be 0. Which is a little bit weird. Because that would be like saying, if I were to draw out a picture, that would be like saying, because if we draw 0, 0, there it is, looks just like a single point, a vector of length 0, so to speak. That would be like saying, this arrow right here and this point right here, they meet at a right angle. They're orthogonal, that means they're perpendicular. That sort of means that the angle between them should be a right angle. That's okay. But what does that mean to say that this little point right here meets at a right angle to the vector? Does that really intuitively make any sort of sense? Doesn't really make much sense to me geometrically. And I think here is kind of where our geometric interpretation of what does it mean for two vectors to be perpendicular breaks down a little bit. And that's, sure, it makes sense to say, oh, this vector and this vector are going to meet at a right angle, because you can see the angle. But it doesn't even really make sense to talk about forming an angle between some vector like this and just a single point. It doesn't even look like there is an angle. In fact, we tried to plug that into the angle formula for, I don't know, let's say this is 2, 3. We would get cosine of theta is 2, 3 dotted with 0, 0 over the magnitude of 2, 3 times the magnitude of 0, 0, which is going to come out to 0 divided by some number times 0. And if there's one thing you remember from taking a class with me, it's this. Don't divide by 0. Terrible things happen. And so here, while we can say that 0, 0 is perpendicular to every vector in R2, geometrically, our intuition of what that means really breaks down. Because now we can't really talk about the angle between the 0 vector and some other vector. The angle does not exist. Because when you plug it into the formula, it gives you a hot mess. Okay, Alex, do you want to ask a question now? How do you do that? Gotcha. Yeah. So here, I would say theta does not exist. You can't have an angle, but you can still technically say they're going to be perpendicular. Because perpendicular really only requires the dot product is 0. So we talked about vectors being perpendicular. I thought it would be good to briefly mention what it means for two vectors to be parallel in Rn. Perpendicular is going to mean that the dot product is 0. Parallel is going to mean that the two vectors end up pointing in the same direction. So we can say that vectors A and B are going to be parallel in Rn if intuitively they point in the same direction. Well, pointing in the same direction is not a very mathematically precise term. What does it mean, for instance, to say that two vectors in R5 are going to point in the same direction? I don't have a good visual intuition. So before I let you guess, how can we make that more precise? I want to draw a couple pictures that satisfy these are parallel, these are not. So I'd like to come up with a better definition for two vectors being parallel that would make it so that these two vectors, for instance, are going to be parallel. These two vectors are not parallel because they don't point in the same direction. And these two vectors are not going to be parallel because they point in the exact opposite directions. So, anyone like to take a stab at how can we more precisely define what it means for two vectors to be parallel? I can guess. They have the same slope. Cool, what does that mean?
They have the same relationship to the vertical and horizontal.
Ooh, okay. So does that mean they have to be the exact same? They have to have the exact same x and y component. So any vector is only parallel to itself.
Just the relationship between that.
How can we write that as something more precise? You're right. You're right. I think that's a good intuitive definition for what that means. It'd be nice to have something a little bit more precise, like something we could just write down with a formula or something.
The dot product has to be a positive multiple of 1. Because then we can get 2 or just scale one positive.
You said a couple different things, so I want to go through each of those. So one of these so first thing you said, I think, was that the dot product is a positive multiple of 1. So basically the dot product is positive.
A whole number.
A whole number multiple of 1. Okay, so would you say those two vectors then are parallel? So I think they would have a positive whole number dot product.
So it has to be the cosine of the angle.
We're trying to relate it back to cosine of the angle somehow. I don't think we necessarily want to actually invoke the dot product on this one. I think that would make it a little bit tricky. But you said something else. What was this? Can you remind me what the second half of what you said was?
They're scalar multiples of each other.
I think that's going to be a little bit more what we're going for, and that we're going to want them to be scalar multiples of each other. So let's say B is a scalar multiple of A. Because multiplying a vector by a scalar typically just changes the length and not the direction. So
I guess the one important thing there, though, would be B has to be a positive scalar.
why positive?
Because otherwise, -1 is a scalar, and so then you'd switch the direction. So if it's positive, you can multiply by an already negative vector, it would still remain negative.
Yeah, I agree. I think we could say that two vectors A and B are parallel if B is a positive scalar multiple of A, or vice versa. A is a positive scalar multiple. We need to force the word positive because if we just said scalar multiples in general, this A and B are scalar multiples of each other, but these are not going to be parallel because they're pointing in opposite directions rather than the same direction. So we're enforcing just, nope, only vectors that point in the same direction. For that, we need a positive scalar multiple specifically.
Sorry. So we chose not to use dot product for this, but hypothetically, would it still be that the dot product has to be equal 1 for them to be parallel? Or are we using this definition for another reason?
I would say the dot product has to be 1 specifically, because these two vectors, I would argue, are going to be parallel to each other, because this is 2 times that. But if you take the dot product, it would come out to 4 and not 1.
Right. Yes. Okay. Sorry.
You could certainly use the dot product and say something about you want the angle between them to be 0,
Yeah.
which means cosine of theta would have to be 1. So you could say something like this, that the dot product of A and B divided by magnitude of A, magnitude of B would have to be 1. I think would be one way that you could do that.
So that was actually where I meant to direct my question, because if we were to use a definition like that, wouldn't the 0 vector, or when choosing this, okay, no, sorry. It would still not be parallel. Sorry.
But the 0 vector is always a bugaboo that kind of ruins your intuition in a lot of settings. Yeah, technically, I wanted to say this because I'd like to be able to say the 0 vector is parallel to itself, which if we tried to use this definition, we couldn't really say because we just get a jumbled mess of 0 over 0 equals 1. So this is the definition I like to go with, saying one vector has to be a positive scalar multiple of the other. Doesn't matter which is which. Because if, for instance, B is 2 times A, then A is just going to be a half times B. And each would be a positive scalar multiple of the other. Sarah, I think earlier you had mentioned you had asked something about how displacement vectors would affect this. And it doesn't matter whether your vectors are displacement vectors or not. We could, for instance, say A and B are parallel vectors if they started at different points. So I would say if this is our vector A, and I don't know, this is our vector B, I would still argue that these are both parallel. Because if you were to write these out using coordinates, B would probably be something like 2 times A. So even if they don't start at the same point, you could still consider them potentially to be parallel. And in fact, oftentimes when we think of the word parallel, we're often thinking about things starting at different points, because when it comes to parallel lines, for instance, which we could say 2 lines are parallel if they have the same slope, typically we're not thinking about lines that intersect each other at all. That they're kind of starting with different points but have the same sort of slope. Which intuitively we could definitely say means the same. They have the same relationship with respect to the x and the y axis, so to speak. But this gives us a nice definition that generalizes to higher dimensions if we have 3, 4, 5, or 10 trillion, heaven forbid, axes. So Dr. Gersel, what can we say if A and B are pointing in exact opposite directions of each other? Like in that third picture over there, or if I did a little switcheroo and did this. In that case, we'd say the two vectors are actually anti-parallel to each other. And so we can say if B is a negative, scalar multiple of A, then A and B are anti-parallel, meaning A and B point in opposite directions of each other. So this would be a case of anti-parallel right here, where one's pointing up and to the right, the other's pointing down and to the left, so that they have a 180-degree angle between them, say. But Dr. Gerstel, with all these definitions, wouldn't the zero vector technically be parallel to itself, anti-parallel to itself, and perpendicular to itself? Yes. Zero vectors weird. Any other questions or comments about parallel or anti-parallelness? So the last thing in this packet I want to talk about is another theorem, meaning another kind of mathematical result that you can prove has to be true in all possible contexts, for all possible vectors and scalars. And that's going to be one that talks about certain properties of how does the dot product work. So let's write this down, and then if we have time, we'll prove one of these directions. So here's going to be the theorem. Dr. Gersel's theorem has vowels in it. Yeah, I like to abbreviate theorem as THM because I'm lazy. So we could say that if A, B, and C are vectors in Rn, the same Rn, and K is any scalar value then we could say several things. First of all, if we were to take the dot product of any of these vectors, say A with itself, we're always going to get some number that's greater than or equal to 0. And the dot product is equal to 0 of A with itself if and only if A is a zero vector. So in other words, anytime you take a dot product of a vector with itself, you're never going to get a negative scalar. You're always going to get either a positive scalar or just the scalar value 0. And the only way to get 0 with the dot product, if you're multiplying a vector by itself, is if that vector is the zero vector. Second property says no matter what two vectors A and B you choose, dot product of A and B is equal to the dot product of B with A. So can anybody tell me what property this means the dot product has? That it satisfies the blank property, since the order in which you do it to the two things doesn't matter. This is a word you might have used before to refer to, say, real number addition or real number multiplication. Yeah, it has the commutative property. It's a commutative operation. Meaning if you take the dot product of A and B, do a little switcheroo, take the dot product of B with A, you'll always get the same result. So next one is going to say that if we take A dot the sum of vectors b and c, we're going to get the same thing as the dot product of A with B plus the dot product of A with C. Saying basically A times B plus C is the same as AB plus AC, similar to that property for real numbers. So can anyone tell me what property this one looks like? And what property is being satisfied here that if we multiply by a sum, that's the same as taking A times B plus A times C. It's the distributive property. Next one's going to say that if we were to take any scalar value, any scalar multiple of A, and take the dot product with that and a vector B, that's going to give us the same thing as just taking the dot product of A and B and then multiplying by that scalar, which in turn will be the same as taking the dot product of A with K times B. So if you're doing scalar multiples and dot products, you can do the scalar multiple and then the dot product, or you can do the dot product of A and B first and then multiply by the scalar. Property E is going to say that if you take the dot product of any vector with itself, that's the same as taking the magnitude of A, quantity squared. Which, that's a pretty straightforward one, since just the magnitude of A is equal to the square root of A dot A by definition. Just square both sides. The magnitude of the scalar multiple of A is just going to be the absolute value of K times the magnitude of A. Meaning, for instance, if I had a vector A and I multiplied it by 2, I doubled its length, then the magnitude of 2 times A is just going to be 2 times the magnitude of A. The magnitude of the vector double is the double of the magnitude. If I were to take a vector B and multiply by, say, -3, how many times longer is -3b going to be than b? In other words, what goes in this blank here?
Three.
It's going to be a positive 3, because we're taking the absolute value of -3. And finally, the last property is going to say that a unit vector, meaning a vector of length 1, that's going to be pointing in the same direction as the vector A, is going to be the vector B equal to 1 divided by the magnitude of A times the vector A. So that in other words, if we had some vector A, let's say this is the unit circle. If I had some vector of length A here, and I wanted to basically take A and shorten it so that its length was 1 instead of whatever it currently is, it would be, I would end up getting instead this vector B here that's just a scalar multiple of A, since it points in the same direction, it's parallel to A, and the scalar multiple of A we would need to take to make it length 1 is just 1 divided by whatever the magnitude of A is. And so this basically is telling us, how does the dot product work? It has all these properties, which means it kind of behaves pretty nicely. It has the commutative property, it has the distributive property. You can pull scalars outside of magnitudes and dot products pretty nicely. One thing I want you to keep in mind, when we say that this theorem holds true for all vectors A, B, and C, it means no matter what you plug in, yes, including the zero vector, all of these equations should hold out to be true, just like these did here. And 3 minutes left. I don't feel like starting cross products. All right. When we come back on Monday, we'll have a quiz over this standard, and then start talking about standard 3, cross products. There are practice problems posted on Blackboard. Most of them are odd, so you can check in the back of the book your answers. I encourage you to try those out if you want a little bit of extra practice using dot products for Monday's quiz. Need that? You all have a good day.